पीछे से कुछ इतना नहीं है।
Oh,
back.
sorry.
Yeah, a slightly higher zoom level on the paper will help.
Okay, I'll do that.
Is that better? All right, folks. One more bell. Huh? Oh, I thought that was loud enough. Okay, I'll do that.
सर नजर कमजोर हो गई है सर उसको जूम करें
Or Zoom. Okay.
I don't know first time I'm seeing is that
Oh, oh.
I need to go and speak out.
Uh-oh. You have to go see yourself?
Mirror पे जा
No, but actually it wasn't blurry earlier. Now it's blurry for me.
I think you have to move a little bit.
All right, guys. I hope you can hear me. We are going to do a paper reading of the Llama paper, the Video-Llama. This paper, the best way to understand it is sort of a logical progression that takes the work rooted in CLIP and then BLIP and then BLIP2 and builds upon those ideas and image bind and builds upon those ideas and applies it to video comprehension also. And to do that, I would remind you what CLIP was. Do I need to remind you guys what CLIP was? CLIP we all understand. Okay. So we'll leave CLIP alone. Do you feel that I should, you remember these are the notes of our paper reading from CLIP. If you remember when we did the BLIP paper reading, we talked about it. How did CLIP work? Just scrape the web. Wherever you see an image with caption, take the caption, that becomes your label. Image is your target. But how do you write encoder, a sentence encoder that will apply to images? Does anybody remember? How do you take an image and create a sentence embedding out of it? Yes, but before that, how do you even convert an image into a sentence?
Alternate caption use that.
No. That is what it should have. That's sort of the output. So just to recap, you remember visual transformer? What do? You take the image and you subdivide it into 16 by 16 pixel patches. Then you treat each patch as a word and the image as a sentence. You remember that? And therefore that becomes your input vector along with position encoding. And then for out, like what you're doing is you want to now train it through the usual sentence encoder technique across like a contrastive laws. And you want to make sure that its distance to its own caption is lower than, because now this image has become a sentence, right? And there is a pretty good insight there. You realize that with language models we are thinking, in a way, in hindsight, it looks obvious, but an image is a visual language, isn't it? It's a visual way of communicating, just like text is a way of communicating. Right? And so if you can do that, somehow encode it, then the rest of the technology comes in. What you did with sentence birth, you can do now with images. Now, if you remember contrastive loss, you needed a triplet. You needed the sentence, a similar sentence, and a random sentence. So given the image, what would be a similar sentence? Caption if you find for that image, right? And what would be a random sentence? Just pick a random caption or something, isn't it? So you got your triplet. So you can use your same contrastive loss technique and therefore create a way of image embedding, sentence embeddings for images. That was the CLIP, right? I think the CLIP, CLI, let me recall, contrastive loss image, what was P for, I forgot, right? Check it out, right? So that was that. And then came the BLIP paper. BLIP improved upon CLIP by using a three loss functions. Do you recall that, guys? Yeah. Oh, first was, if you look at this image, do you notice that, and I'll move fast through this paper because we have done this. And if anybody has forgotten this, let me know. But you look at this image. Do you see that it has been broken up into patches? This patch goes through your standard self-attention and feed forward. Now, this is going to, now there is a text here. Let's say that you have a text, a little girl holding a kitten next to a blue fence, right? That's sort of the text encoding. A text encoder goes to the standard encoder part of a transformer. That is good. Now what would happen? When it goes just through this, it would come out with its own encoding vector. What can you do? The standard CLIP idea is to do a contrastive loss. That was your ITC, image text contrastive loss, right? So you can align the image and text. So let me call this as pillar 1, pillar 2, pillar 3, and pillar 4. 1 and 2 pillars are your classic, with this cross attention sort of suppressed, is your classic CLIP, right? Then what they do, so you have this is one part of the loss function, but it turns out there are 2 more parts of the loss function that really improves upon it. The second part of the loss function that they do is something they call image grounded text encoding. Now, what is that? What is image grounded text encoding? To recap the pillar 3, what you do is you notice that in the standard encoder, you have sandwiched a layer called cross attention layer. In the cross attention layer, you're taking the image vector and you're feeding it in. Image encoding, you're feeding it in and you're hybridizing it with whatever the text encoding comes out from the first attention by self-attention layer. And then this is the cross attention. So in these pictures, whatever comes from the horizontal side typically represents the grounding point. It's almost like, I don't know where they got the terminology, but one trick that I use is think of transistors. You have the base voltage, right? And so forth. So anyway, you're doing this signal then is informed by this image. So it is very different from the text encoding here. It is image grounded text encoding. In the image grounded text encoding, what do? Now you use a matching loss function, image text matching loss function. What does the image text matching loss function do? If an image and a text go together, the captions are true, you want to produce a high probability, right, of a match. And when there's a random text, you want to produce a low probability of match, right? That's it. Yeah. So that will train this loss function. This is just a simple loss function that's just telling what is the probability of its being related. And then comes the 4th pillar. What was the 4th pillar? If you remember, it is basically your autoregressive decoder, right? Token by token by token. It produces is the decoder part of it, except that you have modified this also to have the cross attention. Now you're grounding it with what? Again, image grounded text decoder, not text encoder, decoder. Remember, this is text encoder, this is text decoder, right? Decoder means it will produce one word, then another word, you feed it back, all the token by token, it starts producing. And then what is the loss function for a decoder? Comparing it to what you thought it should have produced, right? The label sentence. That's your decoder. So this was your classic blip that we covered a while ago. Are we recalling this, guys? Does anybody want me to explain it more? We recall this, right? This is your decoder. I mean, this is your blip. So then, what are the benefits of blip? Right. One of the things it did is it helped you clean
that picture. So instead of a 3x3 grid, if you had made a say 4x4 or a 5x just a smaller one, and the kitten was just broken into small pieces, then there wouldn't be a notion that there was a kitten there.
That is right. So in other words, what is the right level of granularity? And by evidence, people are mostly stuck by 16 by 16 pixel or something. Okay. Like that. Yeah. You can do 32, I mean bigger, but don't go too small. Otherwise, there's not enough context. So see, what they're trying to do is each patch is like a word, right? So a word has a meaning. So you want to keep a patch big enough to have a visual meaning. That's one way of looking at it. With this there, one of the side effects of this paper, if you remember, is you could literally use it to clear up the data. So if you look at the clip raw data, there was a lot of mislabeling and silliness people have, most of the time when people write IMG, SRC, and then ALT, they use that more for the search engine optimization than being honest about what the picture is. Right? So irrelevant things are often given, and this example was given. Like here is a picture. Birds are flying in a sunset over a lake at sunset. This is what BLIP generates, whereas the actual caption in the data was from the bridge near my house, which is not something that the picture is saying. It gives an alternative reference point. And so you realize that BLIP, when you look at this result, it's pretty impressive, isn't it? Likewise, when you see this, a potted plant sitting on top of a pile of rocks is more descriptive than in front of a house door in Austria. And sometimes it fails also. For example, when BLIP looks at this image, it says a large building with lots of windows on it. On the other hand, the actual caption was more specific. It was that current castle was built in blah, replacing a blah. But if you think about it, that is a fact that is in addition to what you see in the image, right? So I wouldn't call it too much of a negative. So that was it. And as you notice that when BLIP came out, it right away did an amazing job with the benchmarks. I won't go over that. Right. So now we go to the BLIP2 paper. Oh, by the way, look at this. All of these, I'll just let you stare at the, somebody said, make it a little bit bigger, touch on, so I'll zoom out. Is it looking bigger, guys?
Yes.
Right, so that's how these things go. Sometimes it's right, sometimes it's wrong. Right. For example, you notice that this one, it seems to have gotten wrong.
So it basically the sunlight, those edges, it kind of thought they were halfway, right?
Yeah. So a pretty good result. But there is a problem with this. Do you realize that this is a lot of computation? Like you look at BLIP, and suppose it was a 1-week project for you guys. right? Now would be the time you would want to bail out, isn't it? So this is a pretty like end result of a lot of hard work to put together something like this. So now, what do you do? Then came the BLIP2 paper, and it said that, see guys, why are we using a decoder? So basically the question it asked is, if you look at the 4 columns here, you can put a decoder, the column 4, but these days they are excellent decoders or generative, decoder generates, right? Why not replace the decoder with a full-blown LLM? Are we together? What if you put Llama, Vicuna, Falcon, Mistral, whatever you want out there? Would be far more powerful, but what would be the catch? The catch would be, you can't train it at this moment. All 4, you're training these pillars, all 4 pillars, right? Then you wouldn't be able to train it. But then you ask, is that really a loss? Likewise, you look at the first one, converting pictures to vectors, right? Why are we doing a contrastive loss, image text contrastive loss, when CLIP has already done it and VIT already knows how to create patches out of it, right? Why are we doing that? So what if we said that we froze the 2 sides and said that there are enough parameters in between for it to learn, right? The only weights and biases will change will be the ones in the center. We'll take a really powerful image encoder, right? We'll take a really powerful large language model for decoding. And in the center, we'll put something, the bridge connecting all of them, which is the only thing that you'll learn. Then what? And that is the idea of BLIP2. So let's go to BLIP2. And again, guys, I'm going over this a little quickly, partly because we have a dearth of time. We have to have our presentations starting at 5:30. And also, I want to give you guys time to get ready for it. Those of you who want to present. So then that brings us to the next paper. Is this visible, guys? Is that readable?
Yeah.
So yeah, I'm using my touch finger. So by the way, I hope you guys are not able to see my finger on the screen. Yeah. Okay, good. So what this says is, it uses the concept of a frozen model, which basically means take an image encoder, all its weights, make it non-learnable, freeze it, right? That's why you see that, snowflake picture there, frozen. Likewise, take a large language model of your choice, Llama, Vicuna, whatever it is, freeze it. Then you say that all the learning has to be in between 2 pillars, except that you have one guy there, right? And you say that that is the only thing you can change. Now, large language models are getting scary big, right? Apparently, I heard rumors that there is a 3 trillion parameter model about to come. And there's even some, I don't know how credible the rumor is, that while they'll release a 3 trillion parameter model, there is a 100 trillion parameter model already in the skunk works, right? So things are getting crazier and crazier, right? So when such large and highly competent language generators are there, decoders are there, you just use it, right? And at the same time, image encoders are getting better and better and better. Just use it and only have the in-between thing trained. So the Q-former, to compare the size of a Q-former compared to a trillion parameter model or hundreds of billions of parameters or whatever model, a Q-former, what was the size of a Q-former, guys? Do you remember? In BLIP2? Tiny. By today's standards, practically microscopic. It was just a few 100 million parameters, isn't it? And so you're saying that that Q format just has to be the glue binding two visual languages together, two languages together, text and image, isn't it? It is just an alignment, learning how to align. Am I making sense? Q format's only job is to learn alignment between the two. And aligning it also then thereafter to the language model, feeding it to the language model. Language model stays frozen, image encoder stays frozen. Right? So yeah, so obviously everything is a transformer in this world, right? Everything. So it's a baby transformer. Okay? So now,
So Asif, here you said that write a romantic message that goes along with this photo, right? Instead of along with this photo, if you said that I'm somewhere near the lake with the sunset, write a romantic message about it. Would it write the same poem out?
no, it will write a different poem.
Why? Because I haven't seen it.
No, generally what happens is that even slight, and this is one of the things, usually perturbations of the input lead to small changes in the output. You may get a poem that is almost essentially the same, but the wording may slightly change.
Wording is different. So what?
Semantically, it may be the same.
So if I don't ask it to do any poem or anything, what is the output over there? To just say it's a sun over to sunset over a lake.
That's it. It will come up with a description.
Sunset over a lake.
Yes, and in fact, as we saw in just the BLIP itself, it produces really good descriptions of images. And so by the time you come to BLIP2, it produces, as you will see in the results of this paper, even better descriptions of the images. In fact, the topic you say it is that it is, see, one of the big.
So it is a summary of, so it's a summary of the image versus elaborate even more about this image. It can write.
It can write.
More like this.
No, not it can write. It can answer specific questions. You can ask, okay, so let's go through the examples and we'll see. So it is, so the topic that the point that I was trying to make is, there is a big topic, big field that has emerged. Visual language understanding, VLU. You are entering that. This is, started with BLIP2, but visual language understanding as a field is maturing, literally as we see, as we make progression through these papers. And visual language understanding is literally where your project is heading. Right? So, like for example, and I will relate it to the sort of MRI images that you look at, and we'll talk about that. Right? So, guys, this picture, when you look at figure 2, is it dead obvious what it is happening? What is that cross attention mode? You remember when the text goes and it has to do image grounded text encoding, right? The output of that, even in the previous BLIP, was going to the image text matching, the probability that the two are aligned, exactly the same. The output of that, of this image text contrastive learning results, you're feeding it into generation, image grounded text generation, because this whole data you're feeding into the decoder or the large language model, which is sensitive to the encoding coming from images and text, image informed text or image grounded text encoding, right? And what is the, in total, Q former contains 188 million parameters. Right? No, these days, when you talk of LLMs, where the fashion is to get bigger and bigger, no self-respecting outfit will release a model this small. Right? But this is the magic. So what you have is a Q former is a magical thing. It just, with a very, very efficient transformer, it manages to create alignment, just the right alignment, leveraging the work of others. Right?
So you can create Q transformers for all different types of applications, right? Why it is just image?
Yes, and that's exactly why we are going to Video-Llama. That's the whole point. So this is it, guys. BLIP2 second stage vision language. So I won't go over the paper. We have gone over this many, many times. But let's just look at the results. You ask this image, explain the advantages of this product. And notice, guys, that this is not just captioning it. You're asking it a direct question. You're not even telling what car it is. If I had looked at it, I would have no clue. Frankly, I would not have a clue. And it comes back and says the audio e-tron quattro concept is a plug-in hybrid, blah, 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 that has a range and can accelerate, blah. Tell me something about the history of this place. The Great Wall of China was built in blah, blah, blah. See, it cannot do that. You can say, hey, is the LLM doing that? But how did the LLM know what it is looking at? LLM just takes a prompt and then produces an output. The prompt has to be that Great Wall of China needs, right? What is the history of the Great Wall of China? So the rest of your BLIP2 understood that and fed it into the LLM. Right? Likewise, write down the facts that you know about this flower. Right? And this I thought was really impressive. What are the ingredients I need to make this? And you see this, and these two are really very, very interesting. Look at this picture, right? And you ask, is this photo unusual? And it says, yes, it's a house that looks like it's upside down. Right? How could someone get out of the house? Then it says, it has a slide on the side of the house. Isn't that nice? Right? And for good measure, here's a funny one. What are shown in the photo? A man and a chicken. What does the man feel and why? He's scared of the chicken because he's going to fly at it. In other words, the man is getting out.
So BLIP could look at like images and describe with images. BLIP2 took it to the point of image recognition with LLM.
With LLM, yeah. That's it. So instead of a decoder, it uses the full power of a LLM.
Isn't some
It's by the same guys, by the way. Same guys did it. Yeah.
GPT-4 also does the same, right?
Yeah, they're
That's
bringing
what
in these
we call it.
capabilities. Yeah. See, one thing, and I don't know how true it is. It's anybody's guess because they have never revealed it. The GPT-4, from what I heard, is not one thing in general. It is a sort of a pool of different models, lots of different models to which agent delegates. And so I wouldn't be surprised if this is sitting somewhere in there,
Inside.
or some variant of this is sitting somewhere.
So far, all the examples that you've shown, I mean, even the earlier ones, which were maybe did not capture the right sentiment, but still kind of describe the picture in certain things. But none of them seem to like hallucinate in the way we were talking about it. But do they experience
Visual language? Yeah. See, you're asking short questions and answers. Generally, hallucination tends to become pronounced. So the probability is always there, but it becomes much more pronounced with longer narrators, longer generation. Albert.
So basically, you are getting a better caption for your image, which is more meaningful.
Yes.
Because you have a Great Wall of China. The previous thing would say some wall existing here. You actually know the Great Wall, and accordingly you get a great caption.
That's right. And think about it. You all have images. Do you realize what it means for your personal image repository? Now, you can just run through it and produce little narratives. And you can create a search index. So the search project that you're doing is beneficial to your own personal histories, family histories, and the vast amount of images. See, what happens is we go clickety-click, and before you know it, you have 10,000 pictures. Right? And people like me who are interested in photography and who now have carried these ginormous memories in our DSLRs, right? We go, like sometimes we go shooting a picture, and before we know it, we come back with thousands of pictures in just one photo shoot. Right? Do we ever get chance to get to it? No. But now you can sieve it through the system. In fact, the system that you are building now in your project. So one of the ancillary benefits, French benefits of what you are building is literally you'll be able to archive and better annotate your own images. Right? You could ask questions like, show me a picture of how did I look like when I lived in, let's say, Santa Monica. Right? Then it will pick up a picture of Santa Monica and you there and show you.
It's almost like they have this ask the PDF is similar. It's like ask the question of the picture.
Picture now, yeah. So that is it. So and what is happening at the end of this movie? The Titanic sank rather brief. You're right, but rather brave. Did Leonardo DiCaprio's character survive being drowned? So, as the story goes, I found that funny. It's like very laconic answers, right? And then here's the thing: the narrative quality. Write a conversation between the two animals, and it says, "Hey, cat says, hey dog, can I ride on your back? Dog, sure, why not? Cat, I'm tired of walking in the snow."
So ask it. That one is really short, right? No, he drowned. Is there a reason he didn't give the whole story behind it? Is there a limit on?
No, because it's a very precise answer. Right? The question is formulated in such a way that it admits yes and no as answer. Right? So that was that. That was BLIP2.
So, Asim, I'm just wondering how they are feeding the input to this whole BLIP2. See, here the input is not just an image; it's image along with the
Question. That's what you do. It takes two inputs. It takes a prompt and an image.
I'm just wondering how you feed that to the LLM.
So imagine a simple Python function. First part is an image, the PIL image object, pointed to an image byte file. The other is just text. Both of them ultimately just become encoded vectors. They go through the VIT and the usual thing. If you look at VIT, it will take an image object. So, and all of these APIs are very mature. Like if you look at PyTorch, it literally has PyTorch and so forth, processing. Vision.
So the
PyTorch
same
vision.
would also be for sound as well, right? Almost.
Yes, yes. So we are coming to sound and video, right? So let's go down. So you say, well, now that you have conquered, oh, by the way, this is good. Write a famous quote said by this person. And it says, it recognizes this is Albert Einstein. And it says, the world is a book and those who do not travel read only one page. Okay. Sort of interesting because you stay where you are. And pretty good quote. But you notice the word visual language understanding takes on color when you see examples like this, isn't it, guys? And can I wear this on my trip to Canada in December? Right. Says, well, you can. It's a nice shirt and short, but it's a little too casual for a trip to Canada. Right. But it would be perhaps more precise if it said it would be rather cold there. And so now let's move to Video-Llama that we covered. Right? Why Llama? Remember, one large language model. Right? So it's put in. So think about it, guys. If you want, can you do videos with BLIP2? You can't. You can feed it images only. But the idea is there. All you need is a Q former that will do alignment between a text and whatever other format you have. Isn't it, guys? You just need Q formers for alignment, and Q formers are amazing. They're tiny, easy to train, amazing. Right? You leverage the power of good encoders, image encoders, and you use the power, harness the power of the large language models. Right? So how in the world can we make this happen? these authors say explicitly that they are leveraging this and they are using image bind for sound. They'll explain what it is. So this picture says it all. If you remember, just to give you an idea. First, let me explain what this picture is. What is a video made up of? Video clip made up of? Picture frames, images in a sequence of images, and audio there. Two different artifacts, isn't it? So what you do is, and at this moment you take it, did I cover image? We covered image bind, right? We did cover image bind. So if you pass it through image bind, what will you get? You will get an encoding. Sound will become a vector. That's okay. Or if you haven't done it, just assume that it can do that. Okay. Next, images. Each of the image will get chopped into patches. Right? Each image gets chopped into patches. Those are your, these vertical, like 16 by 16 patch, for example. This is this tower that you look at. Let me call this tower A, B, C, D. Right? I'll put A, B, C, D. Do you see the alignment between the two? This A went through the visual encoder and became this.
Shouldn't be A, B, C, D?
What do you mean by?
The order.
No. Order is the same. The first one is here, second one. Oh, you mean the way, it depends upon how you feed it. It doesn't matter. Like because you're feeding them all together.
Okay.
You're not feeding them one after the other.
The sequence doesn't matter.
There is no sequence. You feed all of them together.
Okay.
Right? Just like, see, remember the whole transformer world's main thinking is forget sequence. We'll just put them all together and do position encoding.
Where they are.
Okay. Yeah, position encoding. So now all of these
you need a lot of vertical towers.
Yeah. If you have, let's say 50 frames, 50 vertical towers.
But if you have like a 10-minute long video?
So the limitation is at this moment, given the computational limit, it is not advisable to feed large videos. Let's just say that the hardware isn't there yet.
Like, because what we're trying to do is give it a video and come back with embeddings on that.
That is right.
But you could always break a big video into small
It's a small video. That's it. That's what they advise. Clip. Feed it clips. A minute clip, 30-second clip.
You can transport it.
What's that?
You can transport the video to make it short, like reduce the resolution.
No. It's the number of
Isn't
frames.
it
Number of frames.
Number of frames.
Yeah, you can also reduce the number of frames.
Frames, yeah, you could do. So you could do sampling, sub-sampling between that and so forth. So so guys, what happens? So suppose here we are looking at A, B, C, ... and D, which means that there are lots of them there. But let's say imagine that there are four frames. Each frame has, let's say, 10 patches. So how many vectors do I get? Encoding vectors do I get? 40. But for each image, you also add its position encoding. It's called temporal. In the world of video, you call it temporal information. Time position, right? Time position, in the time spirit, which came first before the other. Temporal information you need to add, just like the standard transformer. What do? Which word is it? First word, second word, third word, right? You did the position encoding. Here you do the temporal encoding. The same idea, same thing. You inject it. So the first 10 frames, all the patches belonging to one frame will have the same position encoding.
Timestamp.
You can think of it like that, but they don't use timestamp. They use actual vector, but idea is the same. Right? Then what do? You get all these vectors. You feed it through a Q former. Right? What does the Q former do? Remember, Q formers are alignment devices. And you ask the Q former to, given one picture, right, to take all the patches and somehow aggregate the patches and produce, and the position embedding and everything, produce one vector. Right. So your A, B, C, D is there. So video Q former will produce some vector. Right? Now comes an interesting fact. You want to feed it to a LLM, but the LLM, its vector length may be different, isn't it? Input vector length may be different. So what do? What you need to do is, you need to do a linear transformation from one dimension space to another dimension space. Vector of this size to vector of that size. When you're doing a linear transformation, what is the best temptation? What is the temptation you should fall into? While you are at it, might as well throw in some activation functions. Right? So when you see the word linear, it is much more throw in a feed forward layer. You see that, right? Might as well for good measure. And then you feed it in. But now think of the LLM. Now in the right-hand column, right-hand channel, audio goes in, exactly the same thing happens. Temporal sequencing, audio Q former is there. So what are the things that you're actually training in this system? The video Q former and the audio Q former, isn't it? You're training for alignment, and then you feed it into the LLM, and LLM will produce some text. Now, how do you backpropagate? What is it that you can train? What are the parameters that you can train? The Q former parameters. How would you do that? Your labels are, then you can use the standard decoder loss function. What is it that you wanted it to say versus what it said, right? What it generated. And you can use that for the loss and backpropagate and learn. And that is it. That is your, in simple terms. Now the question is, images, yes, you use the VIT and Q former to do that for the BLIP thing. What about audio? Audio, BLIP can't do audio. Okay, no problem. We'll use image bind. Right? That's all it is.
Where do they get the training data for this kind of?
Oh, the world is full of videos.
Yeah.
No, video is there, but we need the corresponding text description.
Oh, it's a lot of manual work.
They actually explain it that for the complete video data set, it's narrower, but they have a lot of data for either one.
Yeah.
But the painful part was the video and audio.
Yes.
They created it. They explained some tools and they.
Yeah. See, guys, behind every good research paper, right, they always explain to you the fun part, the math part, or the discovery part. What is the unsung heroes are the people who sit and annotate the data, who label the data. They are really the unsung heroes. Go ahead.
I annotated.
Yes, there you go. So fun.
Whole day life.
Yeah. For medical data, isn't it?
Yeah.
These are the unsung heroes who are making all this AI possible. Albert.
So how many frames I allowed in that video encoder?
Theoretically, there's no limit, but in practice, people have found that beyond 30 second or 1 minute frame, it gets a bit tough.
So what gets tough?
The computations gets a lot.
But it's the
It's got to be a cascading way, right? See, my point is, I know that temporal, basically what we did is we took a video and we tried to flatten it out into a very wide vector because I have 30 seconds worth of frames and temporal information. So that is some width of parameters, right?
Yeah.
And that's how they kind of describe one object. Like the whole video must be put into that vector form.
Yeah. See, think about it this way. If you put too many frames here, right, this video Q former is going to produce these tokens. At the end of it, each frame is a token. These LLMs, they have a token limit, right? Let's say that you have a token limit of 512. I'm just taking an example. And if you want to divide it equally between the audio and the video frames, then it becomes 256. Now, 256 frames at the rate of 30 frames a second gives you less than 10 seconds.
Wouldn't it just become like a building block? Like, see, when we did the image,
Yeah.
we did cut it into smaller pieces of 16 by 16.
Yeah.
If I take a video
Chop it up.
and I say these are 30-second squares,
Yeah.
and then I can build an even bigger model.
Oh, yes, yes, yes. So people have done that. So this is composition, right?
I see.
People have tried compositions. So, and they're a very active area of work. For this one. So, So guys, this was your Video-Llama. Do you see how easy it was? And we covered this. But one thing that I want to show is, you see how ideas in this field build on top of each other? Good ideas are building on top of each other, right? And this is very like a collective effort. Research is like that, the best ideas build on other ideas. And so then they look wonderful at the same time simple. So this was your Video-Llama paper. So what?
We never use exit data from exit. Like,
That is a very good point. Actually, I don't know. Yeah,
should we,
we should have used that. Maybe somebody
That
has
can be-
used that. Check it out.
new devices, all of them, they have tons of exit.
Except data, yeah. That could have been used, yeah. So guys, was that, are we understanding this paper? And by the way, did you guys actually read the paper? You thought, let's wait for the explanations.
We read
They did, very good. Nice.
right.
Oh, sorry. So I'm going to now pause the recording. And I don't think, can I leave the third paper to be not covered? You guys have read it, it's straightforward. The instruction is very straightforward, right? What I would like to do is just cover the results of this. That will be, and after that, we'll go over to the demos. We are starting with the demos of the of that team, the Optimus Prime transformers. The Optimus Prime transformers are going to do the first demo. So guys, look at the level of sophistication of video understanding. In this video, you have to watch the video to say somebody is opening the door. Describe what you hear. It says, I hear sounds of footsteps on the floor in the background, and there is also a dog barking in the house. Right. Does the man wear glasses? Yes, he wears a pair of glasses in the video. This is the llama saying this. Right. Now, this is a different picture. It says, it's a video clip in which some composer is performing something, or playing something, I don't know. And how was the audience's response? And the audience was really enthusiastic and clapped loudly for the performer. So do you notice, guys, it is not doing a literal, you could have said, hey, clapping, I have a clap detector, right? It is not doing that. There is a lot more understanding of what's going on here. So this field is visual language understanding. What is this man doing? He's playing a saxophone on stage at the concert. Oh, I love this one. This looks like my dog. By the way, I have a golden retriever and she used to run like this. So describe the image in detail. The image features a beautiful and playful golden retriever running on a bright green lawn. The dog is running with a tennis ball in its mouth, and it is an active and lively animal that describes playing and having fun. Right? The green grass in the background creates a vibrant this thing. It is worth mentioning that the dog's focus and dedication to playing with the ball also showcases its natural instincts and its hunting abilities. Additionally, this image captures a fun and heartwarming moment of bonding between the dog and its human companion. That is not visible in the image, and the fact that it can say that, but is implicit in the image, says something, right? Because it's a retriever, it's getting the ball to its owner. Yeah, right. As the dog's positive attitude towards the ball reflects its enjoyment of interacting with its owner and its environment. Overall, the image conveys an inviting and joyful atmosphere. And I can attest to that, having living with a golden
this
retriever.
was given to that stable diffusion or anything that would be prompt like this, would the picture that got generated have the same quality?
Try it out. Try out. Right. See, stable diffusion prompts though are different. They are very unique and specific. They are never narrated.
Right. But we are not too far from going the other way around now, right?
Yeah, you could do that. From that, you can ask a language model to extract a stable diffusion friendly thing. Patrick, would you attest to that? Where's Patrick?
You can use the Excel model to how to do that.
Which one?
The Excel model.
Yes. Yeah, from this narrative, you can extract diffusion friendly prompt, isn't it? from a text.
Yes,
Firefly can do it.
There's another model where you can essentially train the output embeddings to be more instruction tools for.
Okay.
diffusion. That's
I think
another.
Dennis has mentioned something, DXL, is it?
SDX.
SDX.
Oh, SDXL. Yeah, that's just one model. But the actual instructions to send to diffusion from a model like this. But you need like an instruction tuning also.
Patrick, Adobe Firefly will do it, right? So you give the text and it will give you the golden retriever. Adobe
No, but that
Firefly.
is search, no? That is search. Or does it generate?
It's generated. It's generating.
Then it's literally using, yeah, some.
Adobe Firefly.
Interesting, guys. I have Adobe license. I'll try it out.
Give the text.
Okay, guys, this image though has become sort of a benchmark image. Here is a guy. And you ask, what is unusual about this image? And it says, unusual about this image is that the man in a yellow shirt is standing on top of a parked car while holding an ironing board and pressing clothes. You don't usually see that. So it's comprehensibility. Do you know the building in the picture? It says, yes, building is the blah, blah, United States Capitol building. Do you know who the man on the right is? Right. And since I have never watched Game of Thrones, I assume that this is a famous character in the Game of Thrones.
Yeah.
Okay. But by the way, what was the Game of Thrones about? It was to capture a throne? Or what was it about? What's the core idea in that?
Just killing each other.
Killing each other.
How to kill each other.
Oh boy. Okay. I think I would rather
Eventually, it's a kingdom that they want to do. And the only other thing they had was the famous line is winter is coming. So on one side, they assume there's like supernatural, like some powers or whatever.
Okay.
And that's pretty much it.
Oh, okay. Who is the lady on the left? So the lady on the left is blah, blah. What's the relationship between the two? It gives the relationship. I have no clue whether it's right or wrong. Describe
right.
this video. It's right.
So one of the, you're not on record, right?
Yeah, it is being recorded. Maybe later. And describe
I
this
was
video.
worried that what has happened is we kind of turn blind to most of this generated stuff, right? I mean, all the cartoons and things like that. But the young kids who are seeing, they are a lot fascinated by all this generated stuff and not the, like we look at a sunset, we get excited, whatever. I don't think they are that keen. They're more video games and things like that. And what over time will happen is the net will start getting filled up with all these generated images and things like that. And the real pictures that are there will probably start taking the backseat.
Yeah, no, that's a good thing, Sachin. Let's discuss it right after this in the break. But I completely agree with you. Summarize this video in one sentence. The video shows a beautiful scenario. Cherry blossom. By the way, how many of you have seen the cherry blossoms along the Potomac? Do you see? Okay, so and a cityscape with tall buildings in the background. I was going to ask, is it the Potomac? Is it the cherry blossoms from the what direction is the ship going? Blah, blah, blah. That is it. Right? And you can also generate hashtags. So this was another paper generating hashtags. So you can see, you can continue along with it. So guys, that brings me to the project for today. Right? You have to do, what do we have to do? ARAG, that is one. And the project for next week also I'll announce. Right? I want you to do, and I'll announce it. Take our image, create a UI in which you post an image. You can post an image. And you have to create a full narrative about that image, complete narrative, right? That must be a couple of 1,000 tokens long with sections in it.
With ARAG. With ARAG.
And yeah, and two aspects to it is if it has to be, that image has to belong to your domain, it must also augment or benefit from your AI. So use your Video-Llama, take out some things, use that in conjunction with,
Why Video-Llama? That's
oh,
like.
no, sorry, not Video-Llama, sorry, BLIP2.
Okay.
BLIP2, use it in conjunction with something else. Like use compositional effect with different transformers and architectures you've created, and come up with the best narrative. Yeah. If it is about your knowledge, the domain, then obviously dip into your search, take information from there, stitch it all together into a nice narrative.
So this week ARAG, next week BLIP.
BLIP and video.
BLIP and video. It's easy.
Easy, no? No.
I'm still not done with RAG, so I don't know about other people.
No, guys,
No, but-
infrastructure took a long time to set up. You guys have done that. Now you'll pick up steam.
I do have one feedback though, Asif. I think, because I was very new to this domain, I had never done anything over here.
Mhm.
But in hindsight, I think I would have been on top of the project if instead of setting up my own machine,
Mhm.
see, you paid like $5,000 for it.
Mhm.
I think for the duration of the boot camp, if I had a 24/7
Mhm.
running A100 on an AWS, I would probably pay like $2,000. And I understand that's a lot of money, and everybody has to do a trade-off. But I'll tell you that the first 2 weeks,
Mhm.
I just spent time getting the OS up, the driver up, the Kubernetes up, the Ray cluster up. I mean, there was a lot of infrastructure work.
Yeah.
And that would have been a one-click deployment, or better yet, just use any scale.
That is right. That is true. So yes, Satyam has made a very good point, and if I may answer, let everyone know, is that, see, we spend a lot of time in infrastructure and in cloud deployments. These are relatively straightforward. Actually, it was a thing we debated a lot in curriculum development. Lot. One day we would decide, okay, let's just not do this and focus on this, just the AI parts. And then the next day we would say that that is a crucial part of learning. And one reason that I did that, took this route, I knew that you guys will be frustrated. And for a lot of you, it will be the first time you're doing this, especially in the AI world. A lot of you are masters of Jupyter notebooks, right? And this was a new experience, isn't it? How many of you would agree with that? So most of you. And this was a learning experience. So I wanted it to be literally a struggle and a learning experience. But now you would agree that you wouldn't look at what cloud providers are doing as a black box anymore. You would know exactly what they're doing. That was the main point.
Asif,
I don't know if it was the right decision or wrong decision, but it was.
I think you should just have the pros and cons of it, right? See, like I would have rather focused on the 3 weeks on ML and deeper ML than the infrastructure, because I knew going in that Kubernetes is hard, or some of these things are hard, and I ran into problems like GPU drivers and stuff that was painstaking. But I'm not saying bad thing.
But you're ahead of the game than a lot of others.
They're still behind you.
And that's what I'm saying, right? See, when you're trying to do ARAG and you're trying to do like BLIP and stuff, the folks who are behind, I think they'll have a tough time. So I have hope that I'll catch up by next week, but I do understand.
Yeah. So Satyam, just for that reason, as most of you are aware, we have released now the full solution. If you feel that we are too far behind, or infrastructure is not, the setup is not what you want to focus on, start from this week with the solution. Right? That's why I released the solution. See, this was the compromise I come up with, that we will let people learn this whole thing, but in due course of time, 2, 3, 4 weeks later, we'll give them the solution. And if people are behind, they can just start with the solution and start building up from there.
With the solution, you still have to set the infrastructure.
It will do that. It's very easy. So please reach out to the TAs, and we can, like the solution, we can get you running in 15 minutes. On the this Rocky Linux machines, it will run in 10 minutes, 10, 15 minutes. Nothing needs to be done. It will run. Because all it takes is CPU and it runs fine. You can actually run it on your laptop. I mean, assuming that you have a Linux VM, it will run inside that. It doesn't need too much. So anyway, that was a compromise position we took.
And the latest solution that you released is for which project?
It is only for project one because
Project
project multimodal is actually you realize that
Multimodal is very
easy.
straightforward.
You start using it, and hint, some of the things are right here. We're covering it, isn't it? And then comes the RAG. RAG is even more straightforward. What do? You search, you create your instruction, right? As a prompt, you feed it to a LLM, you get the answer. So the RAG part at least should have been, given the fact that each team has 6-7 people, except for one team, Oppenheimer team, every other 6-7 people, and 7 days, that should have been relatively easy. The hardest part was in the beginning, and it was a conscious decision to get you guys to that. So, all right, guys, I'll just stop the recording with this. Anything else anybody has? Or am I even recording? I don't know.
So, Asif, I have one question which is a little out of this, what we are doing here. But as Satyam was asking about kind of launching something on, say, AWS cloud or whatever the cloud of choice, right? Does any one of you have experiences with like the journal websites, site hosting providers, such as, for example, I'm just throwing GoDaddy an example, but do they allow for as much flexibility as cloud providers would in terms of doing some proof of concept deployments, and then basically down the road, I do totally understand that you would have to go down the complete route of deploying in the cloud and going the Kubernetes route and maybe having your own servers at some point.
See, Mahesh, I'll give you my experience. To my knowledge, by the way, there's GoDaddy's, etc. Right? They give you very basic web hosting, like using some all of the standard tools. There is almost no AI support, infrastructure support there. But I may be wrong. I'll tell you what I do. I use GoDaddy simply as my domain registrar, and I just for me it is just a domain name to IP address mapping, right? So long they just maintain my DNS records. I point my mail for that domain to Google Gmail and the Google Suite. I point my website to the machine that I'm running it on, IP address I'm running it on, and that's where I leave it. I never do heavy lifting, or I never even thought it's possible on GoDaddy. So that is the story with GoDaddy, but there are other places. I'm not sufficiently well versed to know what the detailed answer is.
I can share. These are my findings.
Okay.
The best one, I think, that you want to like just get ready and get running, and you're committed to Ray, then it's any scale. Any scale will literally give you like a Ray endpoint. You write code and you say deploy scale. It just works. But then if you want to go into like Ray as a service or whatever, you can deploy a Ray cluster in AWS, GKE, and then there are the cheaper ones, which is like Lambda. There's a new
Lambda
cloud
Labs.
provider like Lambda Labs and a couple more. And all that they promise you is, we can give you a Ray cluster on a GPU, or you can buy a GPU. But if you guys have experience with AWS or GCP or whatever, then you already know how you're doing Kubernetes and things like that. Then it's just a matter of saying, I also want a Ray cluster next to it.
Yeah. Manish, I'll repeat what Satyam said. He said that, see, from his experience, if you want a quick ramp up, just go and you're committed to the Ray framework, then just go with any scale. It makes it very, very easy. And if you want it as a service, they can do your deployment on AWS, Google, and so forth. And there's Lambda Labs also. Lambda Labs is a little quite cheaper actually than that. With Lambda Labs, though, I must interject with my personal experience. Sometimes it's hard to get resources because everybody wants it.
New and cheap and reliability and
hard
all
to
that.
get. I think this was Praveen's experience also. It's a little hard to get.
That's why number one pick is any scale.
Yeah.
They give you an endpoint and you can deploy application.
Yeah. So yeah, any scale, guys, if you are doing Ray, that seems to be the recommendation here.
Thank you, Asif. Thank you, Satyam. That was really helpful. Thank you.
I'll stop.